Hello, everyone. My name is Yanju Chen. I'm from UCSB. Today, I'm going to talk about our work, Tree Traversal Synthesis, using domain-specific symbolic compilation. This is joint work with Junrui, Feng, and Bodik. This work is mainly about how one can automatically synthesize tree traversals in a correct and scalable way. When talking about tree traversals, you may have already realized that they are widely used in many real-world use case scenarios. For example, in compilers, tree traversals are frequently used for many different kinds of purposes, especially for optimizations. In the web browser layer engines, tree data structure is used to represent HTML documents, and tree traversals are the core of layout rendering procedure. In numerical computations, many algorithms are based on efficient traversals of trees. In a word, tree data structures and tree traversals are playing very important roles. So here's a motivating tree traversal synthesis example that I'll be using throughout this talk. Suppose we're trying to automatically synthesize a toy layer engine with simply 2 classes and 4 attributes. As you can see from the right-hand side of the slide, the user can provide an example tree with corresponding class definitions attached. Notice that in the class definition, the user has defined 2 kinds of tree nodes, namely the inner node and the leaf node. If you look at the example tree here, N0 and N1 are inner nodes, while N2 and N3 and N4 are leaf nodes. In the class definition, every class block has 2 subblocks. The children subblock specifies other nodes that the current node can access. For example, the children subblock of the inner node indicates that it can have access to its next sibling as well as its first child. Meanwhile, the rules subblock specifies the attributes of a node that needs to be computed. For example, the inner node has 4 different attributes that needs to be computed, namely W, W1, H, and H1. Here we borrow the notion of attribute grammar to guide the way every attribute is computed. Specifically, every attribute computation rule should be represented by an explicit expression. For example, in line 11, the W attribute of the current node is computed by taking the maximum value between the W0 attribute of itself and the W1 attribute of its first child. Such expression explicitly identifies data dependencies between the related attributes. In addition to explicit expression, by specifying attribute computation rules using attribute grammar, it also requires every attribute to be computed only once during the execution of the whole traversal. We consider such kind of representation more concise and make it easier for problem analysis and algorithm design in our case. In addition, the user could also provide an incomplete version of the traversal, as you can see here. We call it a symbolic traversal. It's essentially a skeleton of the traversal, where the user can specify some higher level structure of the traversal and leave some other traversal details as holes or slots that yet to be filled in the algorithm. The symbolic traversal here defines the behavior for the traversal when visiting different types of nodes. For example, the case block defines the behavior when visiting an inner node. Specifically, the recur language construct will invoke a visit to the target node. Here we first visit the first child of the current node, then we visit the next sibling node. Finally, in line 5 to line 8, we perform detailed operations for the current node. This is a typical post-order traversal, and our traversal language automatically allows the user to specify the various kinds of traversals, including pre-order, post-order, in-order, and many other mixed type of traversals. The symbol tau from line 5 to 8 represents slots that are yet to be determined. They will eventually be filled in with concrete statements. For example, you can see the concrete traversals on the left-hand side, where those lines are filled in concrete evaluation commands of corresponding attributes. So the synthesizer is supposed to figure out what to fill in for the slots in the symbolic traversal. Now you may wonder, why can this problem become challenging? Well, one of the tricky parts is the complex dependencies the algorithm may incur. Here's an example. Consider all the attributes of node N1, where on the left-hand side, you can see 4 trees, where on every tree, I separately draw out the dependencies for every single attribute. Take a look at one of them. For example, H1. You can find out that H1 not only depends on H attribute of the current node, but also depends on the H1 attribute of its sibling. Such kind of dependencies may not be satisfied if the traversal fails to resolve the value of H1 on the sibling node first. In other words, both the traversal and the attribute computation rules place restrictions on how all those attributes can be correctly computed. And such a problem becomes much more difficult when you consider the correctness of the traversal on the space of all kinds of different trees. In other words, on larger trees, dependencies become much more complicated, which can bring a lot of troubles for finding a satisfiable traversal. So there are several categories of approaches for solving the tree traversal synthesis problem. The first category is based on automata. For example, tree filter and grafter utilize deterministic rewrite rules to encode and solve the problem. While you may find such methods a bit difficult to maintain due to the complexity of those rewrite rules. The second category is synthesis-based. FTL is one of the approaches that fall into such category, but it requires domain experts to actually write those constraints for encoding the problem before asking the solver to generate the solution. The manual effort spent here could make the whole procedure error-prone. And finally, there's a third category that utilizes general-purpose symbolic compilation to automate the problem solving. A typical example is Rosette. As you can see from the following figure, where the developer only has to provide a concrete interpreter to tree traversal, and you get a symbolic evaluator almost for free by invoking a procedure called symbolic compilation provided by Rosette. Such a procedure lifts the concrete interpreter from concrete level onto logical level. In particular, given a program which corresponds to a tree traversal, as well as a symbolic input, which corresponds to the example tree, a symbolic evaluator can further compile the whole program into logical constraints automatically, which can be handled by off-the-shelf solvers to get a solution. Even though symbolic compilation is more automatic, it still suffers from the problem of path explosions, and the faithful compilation of all semantics of the interpreter could also result in a symbolic evaluator that generates very complex constraint system. And that's where we step in by incorporating the notion of domain-specific symbolic compilation. So we propose Hecate, a synthesizer that is based on Sige's framework for tree traversal synthesis. Hecate has incorporated domain-specific trace language, and which makes it easier for disentangling complex dependencies in trees, as well as generating easy-to-solve constraints for tree traversal synthesis by tailoring the constraint system in a domain-specific way, while ensuring the correctness. The following figure shows an overview of the whole system. The four main components, interpreter, symbolic evaluator, solver, and verifier, form the core Sige's loop. In particular, the user could provide grammar trees and symbolic traversals as input. And the interpreter compiles the execution of the traversal into a trace program that keeps track of important dependencies during the traversal. The symbolic evaluator then evaluates the trace program into corresponding constraints that encode the problem, which are then provided to the solver in search for a solution traversal. Such a traversal is then provided to the verifier to check for correctness on all potential trees. Hecate will return the solution traversal if it passes the checking of a verifier. Otherwise, it asks for a counterexample tree from the verifier and add the tree to the existing set of trees so as to strengthen the specification. And Hecate will invoke the loop again to search for a better solution. The Sige's loop ensures the correctness of the solution found by Hecate. Here's a syntax for languages for writing attribute grammar and traversal in Hecate. Please refer to the paper for more details if you're interested in the full language design. For the follow-up slides for demonstrations, we'll only be using a subset of the language, which I'll explain when necessary. Since Hecate is built upon symbolic compilation, it makes sense to first understand the problem of general-purpose symbolic compilation. Recall that a general-purpose symbolic compilation faithfully executes the traversal and assemble all the constraints. Here, we still use the motivating example to illustrate the potential problems. In particular, we focus on a smaller subproblem of choosing what attribute to evaluate for the node N1 at slot tau 2, as highlighted in the slides. For this subproblem, the general-purpose symbolic compilation generates a constraint system that contains two parts of the constraints, namely the semantic constraints and the auxiliary constraints. Don't get scared by those formulas, since in this talk, we're only focusing on the high-level idea and won't dig into too much details. But if you're interested, you can always refer to the paper. First, about the semantic constraints. As you can see, the higher level structure is a disjunction of 5 clauses, which indicates 5 different choices for filling in the slot tau 2. So the constraints are basically saying that you should choose one of these attributes to schedule and evaluate for this slot. And next, let's move down a bit into the second level one of one of the clause, say the last clause. The right-hand side of the implication has two meanings. The first row says that all dependencies should have been ready if you want to schedule the attribute on the left-hand side. That is, both H0 of the current node and H1 of the child node should be ready if you are trying to schedule attribute H for anyone at slot tau 2. The second row indicates that the target attribute has not been scheduled if you're trying to schedule it right now. Overall, the semantic constraints capture the data dependencies that are related to every potential attribute that can be scheduled for a certain location. Then there's an auxiliary constraints that mainly focus on ensuring the global correctness of the traversal under the notion of attribute grammar. For example, such constraints requires that every slot should be filled with at most one row, and every row should be used by only one slot, which is straightforward. So far, we've walked through the core constraints generated by the general purpose symbolic compilation. And by a closer look of the generated constraints, you may have already realized that there are a lot of such T symbols invoked in the constraints. They correspond to different time steps during the execution of the traversal. Typically, one slot on a concrete node creates a time step because the symbolic execution needs to choose between all potential attribute computation rows to fill in the slots, and thus creates various paths that add up to the complexity of the constraint system in an almost exponential way, because the current decision being made depends on the previous decisions. Recall that the correctness of the tree traversal needs to apply to all different kinds of example trees. It is unavoidable that total number of time steps will grow as the example tree becomes larger, which will increase the complexity of the whole problem. So we have located one of the major causes for complexity growth. You may then wonder, is there a way to actually get rid of the annoying dependencies across time steps? Well, actually, yes, and that's the reason why we propose the domain-specific symbolic compilation. But before we jump right into that, I would like to take a step back and review the notion of a traversal. Here, I would like to provide a slightly different perspective of how one can interpret a traversal. In our problem, under the notion of attribute grammar, a tree traversal can actually be treated as a Tudor order relation over the set of all locations of a given tree. Let's use the motivating example again. If I interpret the given concrete traversal over the example tree, as shown on the right-hand side, we will get the following Tudor order sequence that indicates the order of attributes of different nodes evaluated one by one. So furthermore, such a Tudor sequence actually encodes the relations between the time steps and the corresponding locations. For example, in the first time step, n4.w gets evaluated, and then in the second, it is n4.h. Such a perspective of the problem actually provides a mapping between the time step and the relational domain, which allows us to get rid of the T variables in the previously generated constraints in the general purpose symbolic compilation. And another good news is, such a perspective also applies to symbolic traversals. All you need to do is just to replace the concrete attribute with the symbols that represent different slots. For the convenience of a symbolic compilation, we design a symbolic trace language that captures the core data dependencies incurred during the execution of a traversal over a given tree. For example, if you want to schedule attribute H at slot tau 2 for node N1, you need to first read the attribute H0 and then read the attribute H1. And eventually you write back to the attribute H1 in N1. Also, for the efficient constraint system, we further convert the generated SMT constraints into IRP constraints. The integer linear programming setting used in our case is essentially optimizing a linear combination given certain constraints. You will see a concrete example in the next slide. Following the same trace program, we now illustrate how it further gets translated into IRP constraints under domain-specific symbolic compilation. The generated constraint system also has two parts, namely the dependency constraints and the validity constraints. For the validity constraints, they are IRP translations of the auxiliary constraints in the general purpose symbolic compilation, but in a more concise form. For the dependency constraints, the previous disjunction gets split into several classes. For example, the first class deals with the dependency between attribute H and H0 on node N1. It has the semantic meaning that N1.H0 should have been scheduled somewhere before the current corresponding location. If you look back to the symbolic traversal on the right, you may find out that all the potential slots that H0 could have been scheduled is only tau 2 and tau 1. So here the keyword B4 gets translated to concrete locations on the traversal by utilizing the Tudor order property mentioned in the previous slide. In this case, as you can observe, constraints are not talking about T anymore, but about domain-specific relations now. The design of such mapping mechanism is done by this kappa operator. So now we can have a qualitative understanding of the complexity of the general purpose and domain-specific symbolic compilations. As what we have analyzed in previous slides, in general purpose symbolic compilation, a faithful interpretation will create dependencies across time steps, which will result in exponential blowup of symbolic states. While on the right-hand side for the domain-specific symbolic compilation, after getting rid of the time variables, the constraint system becomes more concise and will no longer grow even when the size of the tree grows. So in the evaluation, we are primarily interested in the performance of Hecate and its synthesized tree traversals. We'll compare Hecate with state-of-the-art tools such as Grafter and FTR. First, we compare Hecate against Grafter. Grafter utilizes static dependence analysis and generates access automata for encoding and solving tree traversal synthesis problem. We compare the total time spent on finding correct traversals. The benchmark set is adapted from Grafter's benchmarks, which contain 5 representative real-world problems. The table from right-hand side clearly shows that the total problem-solving time for Hecate is way much shorter than Grafter, especially for the harder benchmarks with more rules, for example, AST. Hecate achieved a significant improvement. And as an ablation study, we also create a variant of Hecate that only use general purpose symbolic compilation for problem solving, as you can see here. The comparison also shows that the advantage and benefits of the domain-specific symbolic compilation for simplifying the constraint system. Next, to study the performance of the synthesized tree traversals, we carried out several case studies on those synthesized traversals from both tools. We compare their actual performance on a various number of trees on different sizes. We compare the performance of traversals synthesized by Grafter and different versions of Hecate. Thanks to the flexibility of Hecate, we're able to synthesize traversals that use different data structures, as well as enabling parallelism. The figure on the right-hand side shows the running time of the synthesized traversals, given trees of different sizes as inputs. You can see an outlier from the parallel version of tree traversal given small trees, where the overheads created by invoking parallelism subsume the overall running time. To conclude this talk, we propose Hecate, a novel framework for tree traversal synthesis, which incorporates domain-specific symbolic compilation to generate easy-to-solve constraints while ensuring correctness. The experiments show the advantages of Hecate regarding performance, expressiveness, flexibility, and efficiency. By the way, Hecate is publicly available on GitHub. Feel free to have a try. And thank you for your attention. We're happy to take questions.